Imagine a new world where energy is abundant and free for everyone.
Well, let me talk about the benefit first, so people have an idea of what it means to have fusion. Say you have a few grams of that material, right? The heavy hydrogen and tritium that we use for fusion. Just a few grams, a couple of sunflower seeds. That is enough to sustain a whole household of electricity for your lifetime for 60 years in the United States. So we have plenty of this material, so if we can achieve fusion, it is truly limitless.
At the Lawrence Livermore National Laboratory in California, a group of physicists has achieved a milestone in the pursuit of clean and virtually inexhaustible energy through nuclear fusion. This process, which is the same that powers our sun, promises to be a revolutionary energy source without the radioactive waste of current nuclear fission plants.
What is fusion and why is it so difficult? Fission and fusion were discovered together around 1930s, but we have fission reactors all over the country, all over the world. Fusion, we are still working on it, right? So imagine trying to bring two positively charged particles together. They try to repel each other. They don't want to fuse. So what do we need to do to make that happen? Well, sun is one great example of having the fusion happen. We need great temperatures and great pressures that are really difficult to achieve on Earth.
The experiment used powerful lasers to heat a small cylinder, known as a hohlraum, to 3 million degrees Celsius. This cylinder contains a diamond capsule that houses deuterium and tritium, two heavy variants of hydrogen. The produced radiation vaporizes the capsule, causing the fuel to implode and reach the necessary conditions to initiate nuclear fusion.
Well, it has never been shown before. So far, we have to pump a lot of energy to get almost nothing out during the fusion reactions. So if we in fact can demonstrate that we are breaking through and we're gaining enough energy out of this reaction, then this is a huge, huge step forward.
The scientists adjusted the laser energy and the thickness of the diamond capsule to improve the symmetry of the implosion, a crucial adjustment to optimize the reaction. These precise adjustments allowed the fusion reactions to release 50% more energy than they consumed, a significant breakthrough, although still distant for practical energy generation applications, given that the laser system currently requires much more energy than the fusion can generate.
To get the same type of condition on Earth, we need 100 million degrees Celsius in temperatures and enormous pressures. So technologically, to begin with, it's difficult. But fine, say we have these conditions, now you have to sustain them. How does NIF achieve that? We use giant lasers, in fact, the most powerful laser on Earth, to create enough energy within a very small target. And how that target is designed has a huge impact whether we can achieve fusion or not. The precision that they have to manufacture those targets is down to micron, down to nanometer in some parts.
This discovery not only brings scientists closer to a cleaner and more efficient energy source, but it also provides a model for studying other extreme environments in the universe, such as supernovas.
The problem is that how expensive it is to make this reaction happen to begin with, and now we have to maintain it. And the maintenance of that reaction to make sure it's self-sustaining, that is a big technological problem. So we may see a breakthrough tomorrow, but we're still quite far away from the actual practical fusion power plants.
With constant progress and international collaboration in fusion research, the dream of clean and abundant energy is becoming increasingly close to reality.